for ceramic based nanocomposites, right? Like how to mix raw powders and sintering and compaction, etc. Of course, the hot extraction also we have seen. Today we'll see one of the method called ultrasound assisted method, like, or kind of 1 minute. Why this is coming? Can you see my screen?
Yes, sir, it's visible.
No, someone is also trying to present. Bharatwaj and Pooja Nandakumar. You see here? Sorry. Okay. Yeah. So, so like say for example, you can see here there are some of the nanostructured materials, microstructures, and into that you can also find some of the porous structures present in it. So how to make these kind of structures? I mean, using sonochemical method. So this was the paper. I mean, I've given you for the quiz one. So during the preparation of nanomaterial, you can insert the ultrasonic gun where it vibrates and it produces a mechanical stress into that precursor solution what you are handling. And what usually what it does over the period of time, like I mean the sonochemical process, the bubbles generations will start. I mean there will be a formation of strong cavitation effect. Okay. So, so like once the bubbles started to form, what will happen due to that problem issues with the transfer heat transfer issues? The bubbles will start to break. I mean over the period of time, instantaneously. So once the bubbles started to form during the formation of these crystals, and once the bubbles, broken, the space, I mean, that will become void actually. So that you can fine tune with the help of maybe a 2 second on and 1 second off for the ultrasonic gun, etc. Or you can go with the 2 second off or 3 second on, some sort of those kind of playing with the role of those ultrasonic gun operation. You can able to get different types of porous architecture, because if you do those kind of changes, what will happen? The bubble formation and the rate of bubble start to escape from that portion or the nanomaterial crystals will be changed, and that will affect your the average pore size distribution among your nanomaterials. Okay. And yeah, we do have other ceramics matrix nanocomposite preparation techniques, like solid state routing, like ball milling, and then sol-gel route and melt synthesis and co-precipitation route and hydrothermal synthesis. So we'll see today in detail about the ball milling process. So ball milling process is a kind of process where we use to have a mixture of ceramics. Okay, if you want to mix two ceramics powders, physically, you can use ball milling. And if you want to use some sort of, if you want to reduce the particle size of your ceramics, in that case also you can use ball milling based, high energy ball milling based fabrication process. Okay. So usually what they do, they used to keep all those ceramic powders inside this container, okay, and it will be subjected to high energy collisions from the balls. Okay, this container will be closed and it will be rotated at certain RPM. As a result, this ball and this material will start to collide each other, and yeah, there will be kind of mechanical forging will happen between the particle and your balls. So usually what will happen, what usually does, like you have one container, and then you have one one turn disc actually. So this turn disc will start to rotate, and then your container will start to rotate in the opposite direction. So this is how it rotates. So so this is your container, a turn disc, and this will rotate at one direction, and then your ball and your ceramics mixture, which is inside the container, and they will start to rotate in the opposite directions. So this process will continue for quite long time, and as a result, the centrifugal force will start to created by the rotation of the mechanical align. So this outer one was turn disk, and the inside one is container. Okay. So we have different types of balls, like ceramics balls and steel balls, and then polymer based balls, etc. And the weight ratio between your material and the balls usually like 1:10. And yeah, of course you can also play with those kind of weight ratio, and subsequently you will get those reduction of those particle size or the formation of your ceramics mixtures. Okay. And these are the factors to be considered for this high energy ball milling process. And the selection of ball is very important, and the rotational speed. Okay. And particle size and density media, and the reactivity of the media. Say for example, if you use some media as a surfactant, make sure that they don't react with those kind of balls. Okay. That is called the selection of balls. Say for example, you are using some organic solvent or something, or surfactant which is highly, reactive to the metal substrate or the ceramic balls. Okay. As a result, what will happen? This solvent or the surfactant, they will start to react with the ball, and they'll do all those, contaminations in the ceramics mixture or the nanocomposite preparation. And then yeah, since this rotates at high rpm, if your surfactant or if your material is capable to get flame or fire, then it's going to be a very nasty. There'll be a severe fire accident will happen. So you make sure that the material what you are handling, which doesn't, capture fire at all. And then yeah, the magnetic property is also important. If your material handles, has the magnetic properties, and probably you cannot use the steel balls, rather you have to use some maybe of some ceramics which doesn't have any magnetic sense properties, as well as, or you can also use some polymer based balls. So what if you do overmilling instead of doing 30 minutes? If you do for like 2-3 hours, what will happen? Since this is kind of forging force is happening, what will happen? If we use optimum milling, the macro particle will start to reduce as a small particle, or the ceramics mixture will get mixed well. But yeah, if you do that over milling, what will happen? Since the forging force is happening, there will be a production of heat between these 2-3 particles. So once the heat produces very large and intense heat will start to form, and as a result, what will happen? This kind of aggregate will happen. So a lot of particles will start to bind, together, and they will start to, bind each other, and they make a big particles or the aggregates, so, which is not required. So the objective of ball milling process is to reduce the particle size, as well as if you want to mix two ceramic mixture, to make sure that they are mixing well physically. It's not that they bind together and make a big aggregate of the particle. Okay. So this is one of the case study. You can see like a mixture of nickel and copper based particles. Okay. So they added nickel, like a 5% of coppers. Okay. So you can see here, once they mixed the nickel into the copper, you can see the kind of peak which is slightly, miscible each other or clubbed together. Okay, over the period of time of like 5 hours, 10 hour, and 15 hour, and 20 hours. Okay, this star, the red star belongs to nickel. Okay, and yeah, this one belongs to copper. Okay, so you can see here, once the mixing process started and once it reaches 20 hour, you can also see the merging of these two peaks into single peak. That means the two material or the two particles are completely mixed, and they are attaining those almost close interactions, uh, reached actually. So this is how, they used to study whether the time is optimum or not, like how efficient the mixing was done at certain time. And again, this is some of the macroscopic pictures, like at 0 hour how those particles, and at 5 hours how those particles, and at 20 hours you can see the reduction of the particle size, as well as they are dispersed very nicely, each other. Okay. And this is another one case study. Like they took a fly ash, which is like a byproduct of thermal decomposition of charcoal, etc., which we usually get from the thermal power plant. Okay, so if you see the chemical composition of fly ash, it has got like various mixed oxide like alumina and iron particles, and then silicon dioxide, etc., which are which can be used as a filler or some sort of like additives for metal processing as well as for polymer composite industries. So like this work was attempted to reduce the particle size of the fly ash by using high energy ball milling. So you see here the particle size is pretty much high, like 5 micron, and which was kept under the ball milling for 20 hours and then 60 hours and then 80 hours. And when it reached the 80 hour, you can see the particle size reduction significantly reduced actually. So I'll show you some of the transmission electron microscopic picture of those reduced particle size at 80 hours or the 60 hours. This is how the particle size, it was reduced to 60 nanometers from 5 micron. Okay. And again, you can see the excited spectrum of fresh fly ash and with the ball mill process fly ash. Okay. So you can see the crystal structure, how it changes. Of course, there will be some sort of this crystallinity was also reduced. You can see here there are some of the peaks which is completely vanished when it comes to the 60 or 50 hours of ball milling process. Okay. And yeah, you can also see the crystallite size reductions from fresh fly ash to 48 hours of fly ash. Okay, which can be obtained by using the Scherrer equation. Okay, and different crystals like quartz, mullite, and iron oxide and calcium oxides are present in the fresh fly ash, and which was significantly reduced into the nano level. So those are the story about this high energy ball milling. And now we will see one of the method to produce nanocomposites or the nanoparticles by using chemical reductions method. Okay. So chemical reduction method is also one of the wet chemical route where you're going to produce some nanoparticles or some sort of mixed oxide or some complete pristine nanoparticles. Usually how it starts, they take some metal salts. Say for example, if you want to use hydroxyapatite calcium phosphate based nanomaterial, they'll be using some calcium phosphate based precursors. Okay. Say for example, for the calcium, they can also use diammonium hydrogen phosphate or calcium nitrate based precursors, metal salts. And you have one reducing agents which widely used to reduce those metal salt. And if you want or if you don't want, you can also this is optional, like stabilizers or capping agent or surfactant, which will be used to control the particle size of the nanomaterials. Okay. And of course you can also use some heat energy if you want to catalyze the reactions, etc. And these are some of the typical reducing agent and stabilizers or the surfactant which we use most of the materials like nanoparticle preparation, like sodium borate and sodium citrate and ascorbic acid are widely used for reducing agent, and citrate and the polymeric oligomers and like PEG, PVA and PPG and thiol based agents which are widely used as stabilizers. So what exactly is happening? Like we have three different phases. Okay, the moment when you add those precursors like metal salt as well as the reducing agents, what's happening? The metals, the reducing agent will start to reduce the metal salts into the metal oxides. Okay, so there will be two different types of nucleations, like heterogeneous and then homogeneous and then heterogeneous nucleation. Okay, and once the precursors start to react, and upon this reducing of those metal salt precursors, what will happen? The nucleation will be initiated. Once the crystal nucleation started, okay, I mean, upon the repeating the super saturation of those precursor solutions, what will happen? The crystal will start to, I mean, nucleations will start to growth actually. So then once the crystal, I mean, growth or diffusion growth started, so there will be a chances that, I mean, oswald ripening. That means small crystals or the particles will start to dissolve or redeposit onto the larger crystals, onto the, I mean, nucleated crystals. I mean, so the particles. So in that case, if there is a homogeneous nucleations means you will have a very larger particles. Okay, that means the many small particles are start to dissolve or they start to redeposit onto the I mean another particle, and eventually they will become very larger particles. Okay, if you have the heterogeneous nucleation, what will happen? This will start to grow as a single nanoparticle or the ceramic oxide, and this another nucleated particle will start to grow as another nanoparticles, etc. As a result, you will have a homogeneous, I mean, particle size, as well as you can also reduce particle size if you have the heterogeneous nucleations. So this is how the chemical route, or you can also say precipitation method. Like you can have precursors like reagent 1 and reagent 2, and of course you can also introduce some heat, and by varying the time and temperature, you will obtain the product and byproduct. Product means nanomaterials. So you have phases like nucleation and their growth and their agglomeration. Okay. Initially the nucleation, upon the solution supersaturation, the seed or the nucleation will start to form, and this seed or the nucleated I mean materials, crystals, they'll start to cluster, I mean join together, and then they'll make a primary particles, and then there will be a crystal growth will happen, and that will forms as a particles, maybe of nanorod, or some single, I mean, one-dimensional spherical particles, etc. So there, the once the crystal started to grow, I mean, there the time and temperature, everything is important. Say, for example, if you leave assets, what will happen? They'll start to grow, and the particles start to aggregate each other. So as a result, you will not have those kind of desired geometry of your nanomaterial. So rather, you get these kind of aggregated particles. So maybe I'll stop here. We'll see some of the examples of co-precipitation method in the next class, like how they obtain the calcium phosphate based nanomaterials by using precipitation method or the chemical reduction method. And this one about your Jintal steel course, there is one job has to be done from your side. I thought of will ask Anand, but Anand is not here. Can you do Bharatwaj or Pravan Om Prakash? What the job is that? I think you are taking it, Bharatwaj and Om Prakash. No, the Jintal
So
course.
taking what, sir?
The Jintal steels and I forgot the name.
No, sir.
So Bharatwaj, are you taking?
Sir, where, sir?
No, the Jintal person who is taking on course side. I
Oh,
forgot the
sir,
name.
I haven't registered for that course.
You are not registered?
No, sir, no.
No, for mid semester, yeah, the stainless steels and advanced ferrous alloys. Okay. Okay, I'll talk to Anand then. Leave it. So, fine then. See you on next class. And is there any doubt? And assignment I have seen nobody has done it. What I told you, to make in the table format so that you will have the comparison of different copolymers. But yeah, some of the people